Now let's work on an example to cement our knowledge. Use an actual circuit and the MOSFET and circuit parameters are on your top left. We have also included a small input signal Vi of 150 millivolts peak to peak and has a triangular waveform. Our job is to find all the relevant points on the voltage transfer characteristic, then choose a suitable Q point, and using our calculations, we are going to justify that. So let's start. At point A, Vi equals 1 volt, the value of Vt, and V0 equals VDD, which is 10 volts. Moving on, we go to point B. The first equation is this one. It is derived from this equation here, where Vi equals VIB. Vi is obviously the instantaneous value and VIB is the DC value at that point. Our next equation is this one here. So we are going to solve them simultaneously to get this quadratic equation. Solving it, we get two roots and only one of them makes physical sense, and we choose that, and it comes out to be 1 volts. Correspondingly, at that point, the instantaneous input value is 2 volts. Let me label all these points on the graph. Point C is in the triode region, and we can identify its coordinates as Vi equals Vic equals 10 volts, and V0, which can also be written as Voc, equals 0.06 volts. Notice that this value of the output is very small. Now we have to bias the amplifier to operate at an appropriate point in the saturation region segment. Since this segment extends from V0 equals 1 volt at point B to 10 volt at point A, we choose to operate at VOQ equals 4 volts. Why we have chosen this point will become apparent shortly. We first need to find the current at the Q point, that is IDQ. And this comes out to be 0.333 milliampere. Now we need to find VIQ, that is the input value at the Q point. We find the overdrive voltage to be 0.816 volts at the Q point. And so VGSQ, the value of VGS at Q point, or VIQ, the value of input at Q point, comes out to be 1.816 volts. Using this, you can find the voltage gain of the amplifier, and this is minus 14.7 volts per volt. We could have chosen another Q point, which is V0Q equals 5.5 volts. This is in the middle of the range 1 to 10, and like 4 volts that we had chosen, would have given sufficient output swing when the small signal input was applied. Let's calculate the voltage gain using this. IDQ would have been 0.25 milliamperes, VOV would have been 0.707 volts, and the voltage gain would be minus 12.7 volts per volt, which is lesser than the one for V0Q equals 4 volts, that is minus 14.7 volts per volt. That is why we have chosen 4 as our Q point and not 5.5. Now the input signal, the small input signal that is, it is 150 millivolts peak to peak and has a triangular waveform. However, it also has a DC value. Look at this. That DC value is 1.816 volts. Remember, this is also VIQ, the input voltage value at the question point. So what are the values of the extremities of the input signal? These are 1.891 volts and 1.741 volts. We're going to use them to calculate the extremities of the output voltage when this signal Vi is superimposed on the voltage transfer characteristic. But for that, we must first find the values for the drain current. So let's find them. These are the current values. Let me write them on the graph. Here we are. Look at the graph in the middle and the two blue points. The corresponding current values are written on the current axis. Using these, we now calculate the voltage values. These are the output values at the bottom of your screen. Let me write them on the graph. There you go. Take a look at the two values that are just included in the middle graph. These 2 points are also shown on the graph to your right, that is the voltage transfer characteristic, and I have shown the output swing by coloring the segment blue. And you can see that the extremities of the region lie inside the almost linear segment. That is why our choice of Q is justified. It both gave a large voltage gain and also avoided nonlinear distortion by keeping the output signal confined to the almost linear segment of the graph. You can see that I have added the voltage values on the voltage transfer characteristic on your right.